Good morning. In this class I'm going to continue with my discussion of the Riemann Tensor and derivatives of it. Okay, so I will review what we did the last day. The last day we looked at the Ricci tensor, the curvature scalar, and symmetries of the Riemann or Riemann tensor. I keep calling it the Riemann tensor. It's possibly properly called the Riemann tensor. I explained why the last time. Now, I'm going to eventually number all these lectures in gravitation from Newtonian, number 1, all through Newtonian, then into relativity, general relativity, okay? So that the viewer outside, the public, can track them in order. You can at the moment choose the order by just looking at the date, because they're sequential in terms of date, all right? Time ordered, if you like, all right? Now, I'm not doing these lectures to get hits. Down the road with time, they will get hits. It's not a topic everybody in the world wants to look at. I'm doing it for the record because it's all in my head. I just want to record it. There's more to come. I'm going to go all the way up into quantum gravity using the very simple ideas that I've given you. I'm not going near manifolds or anything weird that mathematicians get bogged down in, and continuities and whatnot. But it's basic tensor calculus, classical general relativity, and you will have these skills. And now at some stage I'll start doing practical examples. When I get bored doing the big theory, I'll start doing lots of practical examples, and then you'll become expert at it. Follow me and you will become quite good at this, right? Okay, so the last time we had the Riemann or Riemann tensor defined like this. It's a commutator of the covariant derivative on a rank 1 tensor or a vector. So the coefficients of this are r mu nu epsilon lambda, the Riemann tensor. And when we contract, that means essentially multiplied by the metric tensor, or sum over two indices. We get the Ricci tensor. When we contract, or sum over, the two indices of the Ricci tensor, essentially multiplying by the metric tensor, or mu means sum over these two indices, we get R, which is the curvature scalar. Then we looked at the symmetries of the Riemann tensor. First thing is, and this one is awkward to prove, it's not difficult, but we have to use the third identity, which I'll show you in a minute. The symmetry between r mu nu, the first two and the second two, exists. Reverse both of those in pairs and we have a positive sign. Both of those objects are similar. Now you actually could prove it just writing it out, the tensor, the Riemann tensor explicitly. Now there is an antisymmetry in the first two indices. If we interchange the first two indices, that is swap their positions, we get to pick up a minus sign. Similarly, there is an antisymmetry. Did I say symmetry? No, antisymmetry in the last two indices. So antisymmetry in the first two indices and the last two indices, and symmetry in the pairs of first two and last two. And then finally we have this one. I told you how to antisymmetrize these indices, and it reduces. We lose all the negatives and we get r lambda mu beta plus r lambda mu beta plus r lambda mu beta, adding them up to give 1. Now it's not quite correct, there's a factor of 1/3 in here. Okay, antisymmetrization. Now in this particular class I'm going to look at this. Now with a little bit of work we can show that this object here, derivatives, I'll write that out in a second, adds up to 0. It's called a Bianchi identity. Now there is great power in the Bianchi identities. I might do a whole class on Bianchi identities. If you look at some, okay, if you want to look at some of the papers that I've done, check up, I studied Bianchi identities in what's called superspace, and I talk a lot about Bianchi identities. There are many applications. You can Google that. O'Reilly, Bellucci, Bianchi identities, okay? Usually get them on spires, but I think if you just look at supersymmetry, I'm not sure what way. I'll get the reference for you later. Okay, let me clear the board and study the Bianchi identity. So the field equations are coming up and the vacuum equations. Now the field equations are essentially what we solve to get either of the following. Okay, a theory of gravitation, you know, let's say, of an object in free space gravitating, or a cosmology in the presence of matter. So, let's look at the Bianchi identities. Well, the Bianchi identities are what I was going to write down there a minute ago. Now don't forget what this symbol means. It's a covariant derivative. Go back and look at the covariant derivative. This is a shorthand notation for covariant derivatives. So this is swapping the covariant derivative 3 times, switching the indices, Bianchi identities. So now we will contract by setting alpha equal mu. Okay, or vice versa, mu will make it. So when we contract or sum over the mu's, an upper and a lower, you have to have an upper and a lower in this index to contract, we get the following. We get a Ricci tensor. We get another one. But I'll swap these two guys and remember the antisymmetry in the two indices, we pick up a minus sign. Okay, there's nothing we can do with the last one yet. So contracting, we get that. What else? Okay, let's contract on beta and nu now. We'll set them both equal to beta. Now that's the same as doing this. It's the same as multiplying by a metric tensor. I'll write it out in full. Now all the time this expression is 0, adds up to 0. So far this is what we've got. Alright, going to, now I'm missing one. Beta, there's a gamma in here. So that's what it should be. Okay. Now remember the anti-symmetry in these two indices. We're going to reverse them and pick up a negative sign. But I have to change this structure first. Now this should be upstairs with the mu. That's what it should be. And I have that object there. Now I'm going to, let's see which way I'll operate with this one here. Okay, this is going to give me an R mu gamma. Now these are dummy indices, the betas, so we can make them anything we want. So I'm going to make the betas mu's. So I have two identical terms, R mu gamma mu. Now let's see. I'll leave that for now. So far I've just got down to these two terms and I'm working with this object here. So I'm going to need board space. Okay. Thirsty work. Okay, so now I want to get an expression where the derivative is a gamma. So I'll use a Kronecker delta. So that's the expression that I get. And it's conventional to put the 2 under this one. So we have that object here, and the derivative we're going to take out separately. I'm going to take it outside the bracket. As you can see, the beta has just been pulled out the bracket, leaving this object here. This defines the Einstein tensor. Which, as we can see, has 0 divergence, and that's a consequence. That's a major consequence. Yes. Okay. Now we can make the tensor look slightly differently. That's another way of writing the same tensor. Or we could write it like this. Actually, I think I'll define it that way. So we'll say this is negative, and this is negative. So this is the positive. Right, yes, this is the Einstein tensor that you see if you open a textbook. That's the way it usually looks like. Yes? Now I'm going to derive some interesting result. We're going to derive, using this, the vacuum field equations, which are quite wonderful. Now in the case of a non-zero divergence, that is in the presence of matter, sources or sinks, we write the Einstein tensor like this. The more general case, well, I won't go into the idea of the divergence yet. In the presence of matter, the divergence ceases to be 0, or might be still 0, but one way or another, these are sources or sinks, sources of their matter fields, and let's see what we can do to modify them. So, that's what the G mu nu is, as we've seen. So we take the trace or multiply by the metric tensor and we get the following. And mu mu's are summed over. Now G mu nu is 4. In the special case of when our space-time is 4-dimensional, which is what we play around with in general relativity, it could be 5 if you're doing Kaluza-Klein, but for our case, 4 is the dimensionality, and the trace of that particular tensor is 4 for that case. And the trace of this we just write as t. And we get the spectacular result that the curvature tensor in this case is 8 pi t. Okay? So let's substitute that back into here. Now is that a negative 8 pi t? No, it's positive. Let's check. We'll substitute in the result. Okay? Let me write this down better here. So far so good. So I have a t here and a t there, and I'll bring this one over onto that side. And that could be out by a minus sign. Where did I put in this minus sign? Okay, this is a positive. This is positive here, sorry. So that's just going to be minus positive 8 pi t negative. Negative. So we get the amazing result that in the presence of matter, our mu nu, the Ricci tensor, is equal to minus 8 pi t minus a half g mu nu t, which looks very like what we saw before. Look at the similarity, okay? So therefore then, what are we going to say? Now something's not quite right here. T mu nu. So far so good. Hence, now in a vacuum, there's no matter present, so T mu nu and T become 0. We arrive at the vacuum field equations, which I'm going to look at. Now, the first solution to these equations was obtained by Karl Schwarzschild in 1916. He was fighting on the Russian front, I think, and did this work under duress, to say the least. Anyway, we will have a look at the Schwarzschild solution at some point, but after this, we're going to derive the geodesic equation, or at least study it, because the equations of motion, under the conditions of after solving the r mu nu equals 0, Einstein's postulate is that the equations of motion will be geodesics in the resulting space-time. Very good. That's our lecture from this morning.